24.0 grams of carbon and 2.0 grams of hydrogen by elemental analysis. What is the compound's empirical formula? Okay, so you all just took a picture. Step one was to do what? Okay, so moles to each element. So 24.0 grams of carbon. Okay. Important thing to note, number, measurement unit, and substance. That is the full symbol. You lose any of those pieces, your answer is wrong. Okay. It said to convert into moles. Moles of what? Moles of carbon. We're sticking to the same substance. This means we would need to get rid of the units of grams. Good thing I'm paying attention today. Of carbon and get moles of carbon in the numerator. Okay. Do I know that conversion factor? How many people actually know that? Okay, so 2 people actually know it. The rest of you that said yes, what did you actually mean by saying yes?
You know where to get it.
You know where to get it. You aren't expected to memorize that conversion factor. You're expected to know where to get it. Where do you get it? The periodic table tells us carbon is, go ahead,
12 grams to a mole.
12 grams of carbon per mole of carbon. Right? This is why the units are there. It tells us where to put those numbers. This isn't divide by 12. This is I'm going to put the units down and let the units tell me where to place these things. That's the power of it. Right? So I can take 24.0. Now I can divide by 12 because I've placed it in the correct location. And I can punch that into my calculator, and hopefully my calculator tells me that the answer is 54, right? No. Okay. What did it tell you? 2. There we go. How many sig figs? We're supposed to have 3. How do you know we're supposed to have 3?
Because the initial is 3.
Our number started with 24.0. All right, do we have to know sig figs? Yes. When do we have to know it? When it is explicitly asked for. Take a look at the practice exam. You will see that. All right. You've done all of step 1? No.
Hydrogen.
It said convert all of the atoms or elements across to moles. So we could go through and do that for hydrogen. What is hydrogen? 2.0 grams hydrogen. Sorry, go ahead.
No, you're fine. And the same thing is just instead of 12 grams of carbon, it's 1 gram.
I'm going to get angry at you. No. I want moles of hydrogen as an answer. That's step 1. Where am I trying to go? I know I'm starting with 2 grams of hydrogen, then what?
So you need to convert hydrogen to moles. Moles.
Grams of hydrogen need to go on the bottom. Moles of hydrogen need to go on top. Now that I know where my units need to go, now I can go ahead and pull what you're trying to pull, which is?
There is 1 gram per mole.
1 gram of hydrogen per 1 mole of hydrogen. Okay, which should set me up with
54 moles.
2.0 moles of hydrogen. Yes? Okay. Have I done step 1? Yes. What's step 2?
Divide mole by smallest mole, and then round or multiply to the whole.
So it says to take those moles and divide by the smallest mole. Which is smaller, 2.00 or 2.0? Officially, it's 2.00. Why?
Because it goes to the hundredths. And
It goes to the
2.0
hundredths
goes to
place. This one, technically, we don't know what that third place could be. It could be anywhere from 1 to 9, for that matter. Okay? So technically, the top one is the smallest. Not a big deal because the numbers are the same. So we can go through as step 2, divide both by the smallest number, which is 2. What would we get?
1.
1. 1 what? 1 mole of carbon and 1 mole of hydrogen. Why is that unit still there?
So we haven't canceled it out.
I didn't cancel it out. Okay. For those of you watching at home or potentially future 151 or 152, there are several chemistry and structures that flip out at this notation. Why might they flip out at this notation?
Now they're the same.
Those are equalities, right, all the way through
Yeah,
this?
you used equalities, you should have separated the, yeah.
So by writing this, I'm saying 24 divided by 12 is 1 mole of carbon.
Right, and that's,
No, that's not valid. Okay, does everybody see that?
you were creating an
Okay.
English sentence, but you wrote a mathematical equation of equalities.
Yes. So officially, we'd have to split this out into a secondary step, okay, just to satisfy anybody who might be watching at home freaking out and losing their mind. Several of my colleagues at multiple institutions. Divided by 2 equals 1 mole carbon. Why is that written wrong? Nope. Sig figs. 1 mole of hydrogen. Now what do? I don't know. Did I put in another step?
Nope, there's only 2 steps.
Ah. So I screwed up.
Yep.
What's step 3? Why did I not put a step 3 in?
There is no other steps.
What I'm making the assumption in is that I already have my answer. I have the empirical formula. Does that look like a formula to you? What does a formula look like?
Words and letters.
There are no words in a chemical formula. H2O would look like a formula, right? H2O. Symbols and numbers. Right? No words. Mole is a word. How can I take that information, 1 mole of carbon, 1 mole of hydrogen, and make that next step to make it look like my chemical formula, H2O?
Each mole and
Well, I know I'm looking at carbon. How many moles of carbon were there according to my calculation?
there's 1 mole of carbon for every
One.
1 mole of hydrogen.
C1, H1. Done. Right? So I screwed up because I didn't include that extra step. You write the letter, the number next to it as a subscript, the letter, the number next to it. We now have a chemical formula. Was that the only possible chemical formula I could have provided as a final answer? Shaking your head no. Why not? What's the other one? I'll accept CH, yeah. I would make the argument that C1, H1 is the same thing as CH, but that's fair. There's another one.
H1C1?
H1, C1,
Doesn't
okay.
really specify which
or
one's first.
HC, yeah. Which of those 2 answers is correct?
C1, H1.
For the sake of this class, both are correct. I don't care. Okay. For the sake of chemistry as a whole, is one more correct than the other? Of course. Because some jerk off went through and sat down and said, that's too confusing. I don't want to look at 2 different ways you could organize those letters. So I'm going to say there is a rule. This is the sequence in which you must put your letters. And I wish I could tell you. I actually don't know the sequence. Officially, carbon comes before hydrogen. I know that much. Okay? So the top one is
We have
correct.
to do it alphabetically.
It's not alphabetical either.
Is it not? Oh, that's
No, it's just weird. I thought it was in the slides, but I may have been wrong. I think it's called the Hall order or something like that, where they went through and they organized how you're supposed to put the letters. Again, not a big deal for the empirical formulas. Don't stress about it. Okay? The order isn't a big issue at this point. The reason it's not a big issue, it's a multiple choice test. We're not going to waste the answer on did you memorize the proper sequence of elements in a chemical formula.
the final's all multiple choice.
The final is all multiple choice. So you don't have to stress about the order. Okay? Yes?
Just so I don't spend like a million years explaining what I'm trying to ask, I did this one, and if you like, get like 2.5, you round it down, right?
What if you came out of this and instead of being exactly at a whole number, like 1 and 1, you were at 1.5?
Round or multiply?
Right? You round or multiply. 1.5.
You round it up.
2?
I heard round up, I heard round down. That's the exact issue. 1.5, that 0.5 is dead in the middle. It becomes very difficult to decide.
Technically, is it
You
anything
have to
above
round down, right?
0.5?
But you can't have 1.5 spikes.
You multiply by 2. What? Why would you multiply by what?
Because then it
2.
becomes 3.
What is 1.5?
Why do you multiply by
Is
12?
1.5 is
Is 3 halves. Why do you multiply by 2? You get rid of the fraction. Okay? So when you go through and do empirical formulas, for the sake of the questions that I ask you, for the most part you come out to whole numbers. On the practice exam, where you had an empirical formula one, you came out to a half value and spot on a half. Okay? You were expected to just multiply by 2. Can chemicals have the same empirical formula? Yes. Okay? In fact, all ionic compounds, right, will only come down to an empirical formula. We never look at a molecular formula. Right? That's because it's an ionic compound. This is why we don't technically refer to ionic compounds as molecules, but instead as formula units. Okay? We're referring to them as formula units because it's the combination of those ions to make a smallest reduced compound. Okay? We look at empirical formulas when we're looking at not ionic compounds. How do I know this isn't an ionic compound?
It doesn't have metal.
There's no metal. It's a nonmetal and a nonmetal. 2 nonmetals is a molecular compound. Okay? That's why we look at molecular formulas for these molecular compounds. Okay? And yes, we can get multiple compounds having the same empirical formula. This is one of the reasons why that technique isn't super helpful. It limits your possible answers, but it still gives you theoretically an infinite amount because you could infinitely scale that upwards. Okay? So that's how we'd get to an empirical formula. It is now the smallest whole number ratio of the elements into that compound. How would I scale that up to the correct molecule, though? Well, to do that, I would have to know some more information. I would have to know how big that actual molecule was. I would need to know, say, its molar mass. So if I take the exact same compound from the previous question, right, I know its empirical formula was C1H1. This question is now saying, I'm looking at a compound that has that empirical formula, but it turns out that its mass is actually 78 grams per mole. How do I figure out what to scale this by? Okay, one option, carbon has a mass of 12, hydrogen has a mass of 1. The empirical formula weighs 13. Okay, so if I increase the carbon, I make it C2H2. Carbon would then be, what would its mass be? 24. Hydrogen plus 2 gets me 26.
I can do math.
Well, that's not right. How about hydrogen, scale it up one more to 3.
This would be 30, or no, it's going to be 40.
And this would be 39. Okay? That works. Yeah, that works. That gets us there. Okay? Eventually. I wish there was a procedure perhaps on your phone that you just took a picture of that tells you what to do.
You mean the molecular formula?
Y
What-
equals, hold on.
Let's not do.
Take your molar mass, 78, divide it by your empirical mass, which was
13.
13. What does that equal?
I don't know.
6. What does that mean? C6H6. Mean that was it? Yes.
Wow.
That's why you have the steps. Right? You're just fitting those pieces in. You can do it long ways and continue to add a carbon and a hydrogen at a time to see what happens. You could condense that. I mean, if you want to be a computer, you can, instead of doing just one at a time, do 2 at a time, see what happens. It's going to cut down on your work. You do 3 at a time, see what happens. If you overshoot, well then back off. Okay? That works. That's fine. Okay? Or you see what that numerical relationship is. It's just a factor of 6. Multiply everything through by 6, you're good. Make sense? Does that work for you, Mario? 78 from the question tells you that the molar mass is actually 78. Does that make sense?
Yeah, that was much better.
Okay. So with that, there's all our steps again. And officially I missed step 4 for the molecular formula. No, I didn't, because multiply the empirical whole numbers by the number from 2. What is 2? Yeah, from step 2. Okay. If I'd written step 2, it puts it on a new line, and I didn't want to do that. So I'd write just 2. Okay? That's your steps. Okay. Actually, let's pause this for a second.
Ionic, polar covalent, non-polar covalent.
Ionic. Awesome. Polar covalent.
London dispersion. I think I don't get this. Do it. Give me typos.
10 what?
Not 10, there's 7. So ionic, polar covalent. I just call it covalent, but we can also call it non-polar covalent. Those are attractive forces. Those forces are so attractive that what do we call all of those?
I know. Electrostatic. Hydrogen.
Those are chemical bonds. Those are the bonds that we discuss as making and breaking when we look at a chemical reaction. Those are the bonds that we look at drawing as lines whenever we draw a Lewis structure. Okay? Those are our bonds. Okay? Wolf listed out a bunch more things. I'm going to pretend I didn't hear him, and I'm going to also assume he's not going to say anything else. And we can try and go with some more attractive forces. We have a dipole, stop. Not just because I can't write that fast, but you're done. Electrostatic. Hydrogen bonding. Dipole.
Like the first one, remember? Yeah, because
Last one? Because I see 1, 2, 3, 4, 5, 6.
London dispersion.
London dispersion.
Which has another name that I can't remember.
London dispersion, aka, I hate writing this one. Induced dipole.
Yeah, you didn't write it in the video.
Induced dipole. Yeah. Any guesses why I think that one's stupid? There's so many freaking letters to write out. I don't think that's fun. Right? London dispersion, I would argue, is even more or is just as irritating to write. What do I write for London dispersion?
LD.
LDF. Ooh, interesting. Where did I drop the F from? These are weaker attractive or attractions than the bonds. What do we call those if they aren't bonds? Forces. They're now just left as forces. Right? All of these attractions are happening between what? Atoms. How many atoms?
Yes.
1 and 1. We are only looking at the attraction between two atoms. Right? Those two atoms can change their properties by changing to a different element. They can change their properties by being chemically bonded to another element. That changes their properties. Right? So we're looking at pretty much an infinite variability for those two atoms, which is going to change the attractive or the attraction between them. If that attraction ends up being really, really strong, then we might classify it as a bond. If it ends up being really, really weak, we might classify that as a London dispersion force. But ultimately, all of these are describing just the attraction between two atoms. And it's now how we change those two atoms that dictates where we fall within this scale. Right? We also want to come up with patterns to allow us to interpret and come through different attractions. Right? This is why we would define each of those and look at the interplay between them. If we look at single atoms on their own, we can fall anywhere within that system, potentially being bonds, potentially being forces. But what happens if the two atoms that I now bring near each other are from separate molecules? Well, they now already have a bond somewhere else, but I'm not concerned about that bond. I'm just concerned about that new attraction between them. Okay? Well, is the rest of their environment going to dictate something about that attraction?
Sure.
Yeah. I want to be able to predict, based off of their immediate environment, their bond classification, potentially something about how they might interact with their outside world. Okay? So how does the bond generate a force? Okay? So what I will first do is look at that atom and classify its bonding nature. Okay? I can use that information with the bonding nature of the other one to then say, well, it can only be this force. Okay, what do I mean? Let's take a look at an extra fun one that for those of you that did the video, I sort of apologize for, because everybody except two people got it absolutely wrong. One person realized their mistake after the fact, and the other person got it right on the first try. What is the attractive force now between that hydrogen and that carbon? Okay, I want to know what that is. Okay, I can immediately now jump to forces. Why can I jump to forces? Okay, it's between two already bonding molecules, but if I had put in a C there, things become a little bit trickier. Is there another hint in this drawing that allows me to say that what I'm looking at is not a bond? How do we draw a bond? A straight line in between them. Do we have a straight line between the hydrogen and the carbon? No, I'm showing a bunch of dashed lines. Is that a bond? No, because I didn't draw it like a bond. So guess what? It's not a bond. That means it's a force. Okay? So let's say it's an electrostatic force. Would we be right? No, we'd be wrong. Okay? We are already pigeonholed by the rest of that structure. The bond characteristics on either side of those define that force. We are now limited by that interaction. As soon as I know that A and B exist, that attraction in between those dashed lines now cannot be electrostatic. Why not? What is electrostatic? Ooh, there's our problem. If we don't know what those things are, we can't classify them. Okay? If I don't know that magnesium is Mg, me writing M on the test is not going to get me any points, because I'm not talking in the proper language. I need to know what those things are first and then apply them. I have to have that practice. Electrostatic. Okay. Electrostatic is looking at the attractive force between charged particles, formally positive and formally negative. Is the hydrogen in A charged? How would we know it was charged? We'd see a symbol next to that hydrogen. We'd see a symbol, in fact, for that hydrogen's charge located where? In the upper right-hand corner. Is there anything there? Nope. So it's not electrostatic because it doesn't have charges. Right? So knowing some rules can help me out. Is it hydrogen bonding? Why not? I see hydrogen, and I have a bond.
Is that hydrogen to hydrogen?
It's not fluorine, oxygen, and
Okay? There are rules behind what makes it hydrogen bonding. As we're hearing in the back, yes, we do have to have a hydrogen. That is an important rule, but we also have to have that hydrogen in a chemical bond to fluorine, oxygen, or nitrogen. Hydrogen just wants to have some fun. Wasn't mine, so that's my excuse. Okay? Carbon is not fluorine, oxygen, or nitrogen. Can't be hydrogen bonding. Dipole, dipole. No, why not? You have to have partial charge. Is partial charge something that you are required to write? No. Partial charge is something that you're supposed to interpret. Partial charge is looking at the difference of electronegativity between the atoms in a chemical bond and saying, where do the electrons in that bond go? Right? I have to have an interpretation there. That interpretation is going to come back to the bond. Whoa, there's a step there for the record. I want to know where those electrons spend most of their time. I'm looking at the electrons in a bond and trying to decide which atom they'd be attracted to. I wish there was something that we've talked about this semester that defines where those electrons could potentially go. It's not Lewis structure. Lewis structure just says there's a bond there. There's electrons there. For those of you that have written down definitions, how good has the definition been helping you? Not very well, because you haven't applied that definition. The definition for the word you're looking for? Electronegativity. Right? Electronegativity is a measure of the electrons being attracted to one atom or another. The larger the electronegativity, the more it attracts those electrons. Right? So we would have to know the electronegativity of carbon versus hydrogen. How many of you memorized the electronegativities for all of your elements? Memorize a little chart thing? You could memorize a trend. Fluorine's the most, cesium's the least. We don't look at francium because it hasn't existed for long enough for us to do anything with. Right? Based on that, we could say carbon and hydrogen are drastically different. Except remember, hydrogen's location on the periodic table is tricky. It could be located in group 1. It could also be located in group 7. Right? Which means hydrogen could be way not electronegative, and it could also be way electronegative. That becomes tricky. How do we decide? Experiment. Really? We got to go to an experiment? Yes. We go to an experiment, we test in that experiment, determine its electronegativity, and then we summarize that information for everybody else to know, and then we tell them, you need to memorize this because it's an important attractive force. And that's going to dictate how that molecule interacts and sees the rest of the world. The difference in electronegativity between the carbon and hydrogen is negligible. What does that mean? Okay. There's no difference in electronegativity, which means the electrons are equally being shared on both atoms. If they're equally being shared, you can't have partial charges. So it can't be a dipole-dipole. It would have to be a London dispersion force. Okay, why? Process of elimination. Did that suck? Yes. I wish there was a better way. Someone went through and said, what happens if I have a nonpolar covalent bond? Well, what is carbon to hydrogen? Holy crap, it's a nonpolar covalent bond? Yeah, it is. every time I take a compound that has a nonpolar covalent bond, the strongest force possible for that compound and how it interacts with the world is a London dispersion force.
So that middle wheel that she showed us.
So the little magic wheel that undoubtedly she didn't understand or interpret because I made it, right, is looking at all of those attractive forces on an entire spectrum and then saying, wait a second, those bonds dictate what type of forces I can possibly get out of the structure. That's why it's organized as a wheel, because we can draw parallels across the wheel for that interpretation. We first have to recognize that there is a significant difference between bonds and forces. Bonds are electrons being shared. Forces, there's no sharing of electrons. We're just saying, you're kind of cool, let's hang out a little bit. Forces are friends, bonds are couples. Right? And there are cases where you can cross over. Electrostatic has charges, also known as cation and anion. Cat what and what? Cat ion and ion. Both of those are ionic. Those would be generated from ionic compounds. Guess what? Electrostatic forces directly correlate to their ionic bonds. And in fact, there's a massive crossover there. Right? Defining whether that is strong enough to be a bond or a force now comes on to the specific instance in which you're looking at. And it becomes very experimental behind how you interpret those. The rest of them become much more straightforward. If you have a nonpolar covalent compound, the strongest force it can get is a London dispersion force. If you have a polar covalent compound, it's polar. It's polar because it has partial charges. Right? With those partial charges, we could now potentially encounter hydrogen bonding. I said if we had a hydrogen, well, hydrogen doesn't have a high electronegativity. What does fluorine, oxygen, and nitrogen have? The highest electronegativities on the periodic table. So I take the highest electronegativities and I put them next to anything, and guess what happens? Partial charges. Hydrogen bonding is a dipole-dipole force. It just happens to satisfy these extra particular requirements. Right? So once we have a way to classify and organize these, it's then a question of how do we interpret. Right? And this is where we run into the why this is important. Your phase transitions. Sorry, my pen's. Relevant to this semester. Right? You're looking at transition between a solid to a liquid or a liquid to a gas. Right? The phase transitions are dependent not on the chemical bond, but on the attractive force between individual molecules. The stronger that force becomes, the more energy is required to break it, which means higher melting point, higher boiling points. The weaker that attractive force, okay, the lower that becomes. Vapor pressure, well, that's a phase transition. Viscosity, that's how those individual molecules attract and move around each other. What's going to dictate that? The forces between those molecules. Less important for this semester. Surface tension, same deal. Big ones, solubility. Solubility is a huge one for this semester. How do those compounds dissolve in another thing? Right? This is why we had solubility rules. We could be doing interpretation of forces and try and apply those forces outwards. Right? And it works to a certain extent. Right? Reactivity doesn't show up this semester, but largely organic chemistry, that's all you do. That big old colorful wheel, that's all you do in OChem? Yeah, that's all you do in OChem. And every organic chemist is going to complain, well, no, there's carbons and hydrogens and oxygens and they change their bonds. You mean they changing their forces between each other depending on their charges? And that's how it's dictated? Yes, yeah. Everything we do in OChem as far as predicting reactivity is now just an application of intermolecular forces and bonds. It is shocking how much just boils down to electronegativity. This becomes cool because I can now predict, does this compound dissolve? Yes. Does this compound react with this compound? Nope, because the bonds and forces are too strong, they won't do it. There's no more looking at an equation where someone already solved it and now saying, well, because you solved it, I can predict all these things. I can look at it and say that reaction shouldn't happen based off of applying those forces. That's where this gets neat. That's where chemistry becomes fun, because it's now how do you build things? Right? Based off of some simple rules of electronegativity, how do we build and scaffold things larger? Not how do I quantify each of those steps, but how can I do this? Right? So, let's look at some questions. Melting point and boiling point. Where are we? Predict which compound has the higher melting point. Okay. Well, this is going to come back to, again, our colorful wheel. It's our phase transition. So for a melting point, what are we talking about?
Making a solid a liquid?
The solid needs to become a liquid. So if I drew out a solid, that would look like a solid, right?
Sure.
What would the liquid look like?
Bunch of separate squares, really close to each other.
What changed?
How well they're bonded together.
How well those individual molecules are interacting with each other. Whoops. That red box is a molecule connected next to that blue box, which is another molecule. What is holding those two molecules near each other? It's now a force. Okay. The bond is what makes that red box a red box. Everything that makes that box red is now a bond. But the instant I look at that unit and how it's connected to another unit, that is now no longer a bond. It's a force. It's a separate unit. It's a separate molecule. This is why we have intra within the structure and inter between separate structures. Our melting points and our boiling points are based off of between separate molecules. I'm looking at the force. Right? Well, what would cause my melting point to be really high?
Strong forces.
I would need to have a very strong attraction in between those individual units so that they cannot be ripped apart from each other. Okay? What is the strongest attraction I can have? Yes, that was a tricky question. Okay. The strongest attraction I can have is covalent. What's the problem with covalent? It's a bond and not a force. So while that may be my strongest attraction, I need the strongest attraction that is not a bond. Well, is polar covalent? No. Ionic? Ooh. As soon as I switch from across that line, from the bonds to forces, I now have ionic. Is ionic a force?
No.
Yes. It is also a bond.
That's both.
It is both, which is confusing as all get out. This is why some people, and I only learned this recently, have cited or are attempting to switch the ionic force from being ionic to electrostatic. This way we can change our interpretation a little bit. Okay? Notice that when we moved through this, we started at the covalent, which was at the bottom. Okay? Remember, what we're looking at is an unfolded line for all of our attractions. Covalent is the absolute strongest. London dispersion is the absolute weakest attraction between them. Why fold it into a circle? So that if I have a covalent bond, I know that that correlates to a London dispersion force. Okay? So we are constantly oscillating between the fully extended straight line, just attraction between these, and now the looped back on itself so that we can do an easier interpretation between them. Okay? And that it is not two separate things. They are the one and the same. They are the strength of the attraction. We arbitrarily decided right through the middle of the ionic interaction that sometimes that's strong enough to be called a bond, sometimes that's strong enough to be called a force, or weak enough to be called a force. So the strongest attractive force is now going to be this electrostatic. So if I want a really high melting point, I want to see an electrostatic interaction. Well, how do I know I have an electrostatic interaction? I'd be looking at dashed lines between a positive and a negative, right? If we flip back, and I'm not going to do it yet, if we flip to that next slide, you'll notice that we're not looking at a dashed line, we're just saying two compounds. Compound A, compound B. How can I apply that then? What I will do is draw out the Lewis structure and look at that compound and say, does it have an ionic negative? Does it have an ionic positive somewhere in the structure? If it does, then when I take those two molecules and bring them near each other, the force between them will now be electrostatic. Does that make sense? How would I know by looking at the compound that I would have positive and negatives? What is a positive called? Cat what? Ion. Where do we get ions from? Ionic compounds. How do I know I have an ionic compound?
I have a positive and a negative.
I could go through a positive and a negative. That's not going to be very helpful because we just said the positive and the negative are buried and hidden. So we can't use that. How do I know I have an ionic compound?
Metal and a non-metal.
Metal and a nonmetal. So I would look at my compound, the formula itself, and say, is there a metal? Okay? Is there an ionic bond in that compound? Yes, then it has electrostatic forces. It's a one-for-one connection. Okay? What if it doesn't have or ionic bonds? Okay? Well, then I would want the next strongest force, hydrogen bonding. The only way I find out I have hydrogen bonding is if I know I have partial charges. How do I know I have partial charges? I would have to define them based off of electronegativity. The electronegativity of the elements found where? In the compound. You mean in the bonds? Yes. What would you have to do? You would have to look at your compound, its Lewis structure, and find polar covalent bonds. If there's polar covalent bonds, now you have the potential for having hydrogen bonding. Right? Does that mean you have hydrogen bonding?
No.
Chelsea should shout out right away, no. And we got Evan down in the opposite corner saying no as well. Why no?
Because we don't know if there's a hydrogen.
Hydrogen bonding requires the presence of hydrogen physically bonded to fluorine, oxygen, or nitrogen. Right? So it's a question of looking at your compound and evaluating its structure, looking at the bonds, applying what those bonds mean. Right? So let's take a look at 1A. Let's draw out its Lewis structure, which, because you guys have done it in lab, you should be awesome at this. There's A. First bond. Is that ionic? Why not? No metals. Okay. Is it polar covalent? No, why not? Say that again. How do you know what a polar covalent bond is? We knew what the ionic one was. How do we know we have a polar covalent bond? I would hope we'd come up with a definition. We did come up with a definition. That definition in the video says it is anything that is not ionic or non-polar covalent. Awesome. It's not ionic, so that means it's polar covalent. No, because I also have to apply, is it non-polar covalent? How do I know it's non-polar covalent? Non-metal and a non-metal, which also happens to be the definition for polar covalent. So that definition doesn't work for us. Try again. Same atom to same atom. Nonpolar covalent means they're sharing electrons equally. Well, if it's the exact same element, their electronegativities are equal. By definition, they're sharing electrons equally. Is hydrogen and carbon the same atom? No, so it's polar covalent. No, dang it. What's our rule? Right? There's two rules for nonpolar covalent. Same to same and carbon bound to hydrogen. Right? Because carbon bound to hydrogen has been found in the experiment to act like a nonpolar covalent bond. Which means carbon bound to hydrogen is not polar covalent, it is nonpolar covalent. Right? I now know that bond. It is nonpolar covalent. What is the force?
London dispersion.
This goes to London dispersion force. Bond number 1, done. Next bond, going clockwise. Carbon bound to hydrogen, is that ionic? No, is it polar covalent? Why not?
Because it's hydrogen and carbon.
It's hydrogen and carbon, which is a non-polar covalent bond. Which means what force?
London dispersion.
So that applies.
Next bond.
Same.
Same. Next bond. Next bond. Next bond. Next bond. Next bond. They're all the same. Yes. Should you be doing this for every single one of those bonds? Yes. This is practice. This is how you get better. Does it suck? Yes. Okay? Usain Bolt didn't just wake up one day and be like, I'm going to be an Olympic sprinter. That didn't happen. Dude went running a lot. Okay? Practiced to get that good. Okay? We have to do the pain of practice. Did I classify all of the bonds? No. What does that mean I have to do? More classification. How about that carbon-carbon bond?
Non-polar, same.
That bond is non-polar covalent because it's the same atom to the same atom. What type of force would that be? London dispersion force. How about the next carbon to carbon? Same thing. Ah. All that, and all you're telling me is the only force in that compound is London dispersion. Yes, that's exactly what I'm telling you.
Oh, well, that makes sense.
Right?
Hydrocarbon chains are non-polar.
Hydrocarbon chains are nonpolar. So you end up with these weird rules that usually biologists throw out. Right? Hydrocarbon chains are nonpolar.
Well, that makes sense.
Kind of, sort of. Not always. But for the most part, they're very nonpolar. Why are they very nonpolar? You evaluate all of the individual bonds in a hydrocarbon chain. What kind of bond are they? Nonpolar covalent, which then means London dispersion forces. Okay? By definition, nonpolar. Okay? The rules that you're told to memorize have a meaning. This is the meaning. Okay? Make sense? Okay, so here's what we're going to do, because I picked the wrong one. I forgot that this list goes in reverse order. Whoops. You tell me the bottom three. Go through, spend some time, figure it out. Find the most polar bond, find the strongest force, and decide which of those compounds should have the higher melting point. And if you got questions, raise your hand. So, if we go through and take a look at these, we can go through and evaluate by breaking each of those structures down into their Lewis structure, or each of those formulas into the Lewis structure, and draw all of those bonds out. Okay? That was tedious. That is practice. That is part of the process of getting good at this. The next part is trying to simplify and cut things down. Okay? Some people have already started to do that. To identify the strongest force is an electrostatic force, and that strongest force comes from the weakest bond. The weakest bond is ionic. To have an ionic bond, what do you need to have?
A metal and a non-metal.
A metal and a nonmetal. Are metals easy enough to distinguish from nonmetals?
Yeah.
Yes, based all the way back on day one of the semester. trying to differentiate those and find that pattern in the periodic table. If you don't know that difference, you've got a lot of work to do. You're looking at the staircase, left of that staircase is metal, right is non-metal. Sodium happens to be
Metals,
a metal. Oxygen is a non-metal.
making it this one is.
We then have an ionic bond. The ionic bond results in the electrostatic force. The electrostatic force is so strong that it starts to become an actual bond. Right? That being then the strongest force is going to suggest that this compound is going to have the highest melting point. If we go through and take a look at 4, we don't have any ionic structures, so it's now looking for any kind of differential. What we'd be looking for is something that's electronegative. So not carbon or hydrogen. Oxygen being right in the middle there, second most electronegative element. The bonds it's going to have with the carbon or the hydrogen are both going to be the bonds, polar covalent. Okay. And at that point, I could immediately stop because the strongest force coming out of polar covalent would be hydrogen bonding, which is weaker than the electrostatic. I'm already done. I don't have to define what 4A is because it's by definition weaker than 4B. 4B will have the higher melting point. Okay. For your practice, go through and do that. You have 3, you have 2, and you have 1. Yes, we will see this again on Wednesday.